Hello kids, I'm Ben and these are my team members Aravind and Carlin. We are Project Team Group 6 and today we're going to show you how we built a solar charger and used it to feed power to a virtual battery.
To do this, we'll be arranging each of our systems in parallel configuration. For good performance, it's important we all have consistent voltage and power outputs.
There were four main components to the design. The hardware being the solar panel, the circuit and the cooling structure, and the software which included LTSpice and LabVIEW. The solar panel. We slapped our multimeter and temperature probes onto our panel and watched our panels in action. Then, keeping those numbers in mind, and taking our given datasheet for our particular panels, we threw together the IV and calculated the short circuit current, the open circuit voltage, the series resistance, the shunt resistance, the saturation current with this formula, and the ideality factor. The circuit. The circuit is made up of three parts: the oscillator, the comparator, and the boost circuit. Sounds simple enough, especially when you put it on paper. And then when you put it together, this is what it actually looks like. To find the best components, we ran simulations switching out different components and found an increased output efficiency in our boost circuit.
To ensure low current ripple and a high power output, we selected a 680 microhenry inductor. We also selected a 1 nanofarad capacitor for our oscillator circuit. That way we optimize the switching action of our boost converter and reduce resistive losses when our inductor is in operation.
Replacing old wires with fancy new wires also reduced breadboard resistance, giving us a tiny bit more juice. The cooling system. When we first threw our panel at the sun, we noticed a temperature dependence. The hotter it gets, the less hot our results get, if you know what I mean. And so we each built structures in hopes of cooling our system to allow for maximum efficiency. Ben and I built ours using Lego, while Aravind was a little more creative and resourceful, whacking his panel onto a tennis racket and using horizontal railings on his balcony to his advantage so he could change the angle of his panel to the sun. All three designs allowed airflow onto the panel to whip away some of that unwanted heat. Slapping aluminium foil onto the back of the panel also drew away heat from the panel faster, allowing for more rapid cooling. LabVIEW and LTSpice. The simulation I mentioned before was done on LTSpice, a circuit simulation program which allowed us to run our circuits with lots of parameters without the tedium of switching components back and forth in a real-life circuit. In order to read data from our real-life circuit, we used an Arduino Uno board to interface with LabVIEW, and so our circuit was totally dependent on our only Arduino Uno board to input data. What could possibly go wrong? We built this LabVIEW system to get data from the circuit and send it to the cloud, designing it to be easy to read and easy to use.
Okay, it's final testing day. We did the practice run yesterday, so it should be alright. I think it worked yesterday properly, so we'll see how that goes. I've got my emergency notepad and calculator. I've got the dashboard and LabVIEW all set on my laptop. I've got my multimeter just in case anything goes wrong. Just behind my laptop, I've got my boost converter circuit, oscillator, my Arduino, and that's my solar panel mounted on my tennis racket. Yeah, that's pretty much it.
We slapped everything together and threw it at the sun again, and that's where our first problems began. If everything went according to plan, we'd have 3 running circuits with half a watt each, giving us 1.5 watts. Our actual performance, though, was quite far from that. Remember when I said about the circuit being totally dependent on the Arduino? 2 of our members' Arduinos decided to fail and read little or no data from the circuit to LabVIEW, which left us with 1 circuit to carry the team's performance. That 1 circuit would also only produce a maximum of 370 milliwatts. That's 0.37 watts.
So we had issues. Arduino problems aside, the remaining circuit still wasn't performing. We suspect the breadboard resistance might have nudged our output power efficiency down a little further, but also the cooling system wasn't performing to standard, with wear and tear damaging the aluminium foil and slapping our power output down even further.
Despite our underwhelming performance, this project really revealed the nature of teamwork, especially in the light of the global pandemic. Each of us had to carry our own weight, and our team pulled through where it mattered. Despite the challenges faced throughout this course, the real treasure was the friends we made along the way. Thanks for joining us through our tumultuous journey through SOLA2051, and we hope to see you all in SOLA2052 Design 2000.